Welcome you all. In this session, we are going to discuss in detail about the choice of specific loading. So the choice of specific loading means we have two types of loading. One is specific magnetic loading and the second one specific electric loading. So specific magnetic loading is represented by B average and specific electric loading is represented by AC, or in some cases we used to represent it by Q. So B average is equal to P phi by pi dl, and electric loading AC is equal to Z Iz divided by pi d. So this is the formula to calculate the electric and magnetic loading. Okay, so in the previous session, in the output equation, after deriving the output equation of DC machine, we concluded that the size of machine depends on main dimension, and the main dimensions of machine depends on the specific magnetic and electric loadings. So while choosing magnetic and electric loading, so it must be very careful while selecting these loadings. So based on this, the D and L value get varies, and again based on D and L value the size of machine get varies. So they are directly proportional. So they are independent. They are dependent to each other. So while choosing a specific magnetic or specific electric loading, certain things need to be considered. So first let us see the specific magnetic loading. So the first parameter is iron loss. A high value of flux density in the air gap leads to higher value of flux in the iron parts of machine, which results in increased iron loss and reduced efficiency. Second parameter is voltage. When the machine is designed for higher voltage, space occupied by the insulation becomes more, thus making the teeth smaller and hence higher flux density in the teeth and core. Next parameter is transient short circuit current. A high value of gap density result in decrease in leakage reactance and hence increased value of armature current under short circuit conditions. Stability. The maximum power output of machine under steady state condition is indirectly proportional to synchronous reactance. If higher value of flux density is used, it leads to smaller value of turns per phase in armature winding. This results in reduction value of leakage reactance and hence increased value of power and hence increased steady state stability. So the next one is parallel operation. The satisfactory parallel operation of synchronous generator depends on the synchronizing power. Higher the synchronizing power, higher will be the ability of machine to operate synchronism. The synchronizing power is inversely proportional to synchronous reactance, and hence the machine designed with higher value of air gap density will have better ability to operate in parallel with other machines. So the next one is specific electric loading. So the specific electric loading. So the electric loading is given by Z Iz divided by pi d. The following are some factors which influence the choice of specific electric loading. So the first parameter is the copper loss. Higher the value of Q is nothing but specific electric loading. So in some cases we used to represent it as AC, or in some cases we used to represent it by small q. So higher value of Q, larger will be the number of armature conductors, which results in high copper loss. So the AC value must be less as per copper loss. This results in higher temperature rise and reduction in efficiency. voltage. A higher value of Q can be used for low voltage machine since the space required for insulation will be smaller. Synchronous reactance. Higher value of Q leads to higher value of leakage reactance and armature reaction, and hence higher value of synchronous reactance. Such machines will have poor voltage regulation, lower value of current under short circuit condition, and low value of steady state stability limit and small value of synchronizing power. Stray load losses. With increase of Q, stray load losses will increase. Values of specific magnetic and specific electric loadings can be selected from a designing data handbook for silent and non-silent pole machines. So, from the above statements, so we can say that for DC machines, the value of B average, that is specific magnetic loading, lies between 0.55 to 1.15 Weber per meter square. That is BG, maximum flux. So for DC machine, the maximum flux varies from 0.55 to 1.15 Weber per meter square, and their corresponding values of B average, that is specific magnetic loading, varies from 0.4 to 0.8 Weber per meter square. So we can say that for any DC machine, the B average value or specific magnetic value lies between 0.4 to 0.8 Weber per meter square. Similarly, for specific electric loading, for a DC machine, the value of specific electric loading Q lies between 15,000 ampere conductance per meter to 50,000 ampere conductance per meter. So, for DC machine, the value always lies between specific electric loading Q value always lies between 15,000 to 50,000 ampere conductance per meter. So now comes the separation of D and L. Inner diameter and gross length of stator can be calculated from D square L product obtained from the output equation. To separate, suitable relations are assumed between D and L depending upon the type of machine we used. So if it is silent pole machine, in case silent pole machine, either round or rectangular pole construction is employed. For DC machine, usually we go for square shape pole face. Okay, so is employed. In these types of machine, the diameter of machine will be quite larger than the axial length. So for if you take the D and L value for DC machine, it always comes within 1. That is, it will be always point values in terms of meter, whereas for alternators, it will be little bit high compared to other machines. Thank you.